morning class and welcome to another lecture in sustainable energy technology. In the previous class, we had started our discussion on energy storage and other associated technologies that are essential to the development of a grid which can absorb renewable energy technologies. In the previous class, we discussed certain aspects of the energy demand and how that demand requires different type of power plant designs. We looked at the demand profile of certain cities and we saw that the energy demand or the electricity demand changes significantly from 1 hour to the other and also it changes with seasons, whether it's winter or summer. This creates the need of multiple types of power plants. We discussed 3 basic classes. The first class was the base load power plants, which are supposed to run 24/7, providing a constant source of electricity at a very high efficiency. This caters to the minimum base demand which is present in a certain location at all times of the day. Beyond that, we had the cycling power plants which are switched on and off at different times of the day in order to cater to rise in demand, like in the busy evening hours or when the AC demand peaks on a hot summer afternoon. These are the cycling or the intermediate load power plants which can be switched on and switched off on a daily basis and can run for half a day or 1/4 of a day. Beyond this, we have the peak load power plants that are switched on and switched off relatively quickly and are small capacity power plants that cater to sudden fluctuations in demand that can happen due to other unforeseen factors. These are called the peak load or the peaking power plants. So if we look at the total energy demand on an hourly basis for a certain location, we will see a graph like this. So let us draw this graph first and then we will explain this. So here is the hourly demand of electricity in megawatts. So the idea here is if we source a certain location, say a certain state in India or a certain state in US or a certain state in France, and we see what is the demand of that state on an hourly basis, okay, and we collect that demand and this demand is plotted on the y-axis. On the x-axis is the hours in year. Okay. Now the total number of hours in a year is 8,640. So we will get, so suppose this is 0, this is 2,000 hours, this is 4,000, this is 6,000, this is 8,000. Okay, so this is the total number of hours in an year. So what we are doing is, we are separating out the year in terms of its 8,640 hours. And we see what is the average power demand in a given hour of that year. So for example, let us say the 100th hour, say maybe this may be like the 3rd of January, maybe 9 a.m. to 10 a.m. That is the 100th hour, right? That hour had how much electricity demand in megawatts on an average for that period of time, for a certain state. That we plot and the y-axis. So year 100 hours, y-axis. Okay. So on and so forth we plot, and then we arrange these hours in the order of increasing demand. So for example, suppose we see that so let us draw the y-axis once and then we will discuss this point. Suppose this is 10 to the power 4, 10,000 megawatts. This is 3 into 10 to the power 4. This is 5 into 10 to the power 4, and this is 7 into 10 to the power 4. Okay. So 70,000 megawatts, 50,000 megawatts, 30,000 megawatts, 10,000 megawatts. Okay. Now we arrange these hours in the decreasing value of demand. So the plot will look somewhat like this. Okay. So what this plot is basically saying is, say, for out of the 8,640 hours in an year, there are at least 2,000 hours in which demand exceeds 50,000 megawatts. That is, demand is varying from 70,000 to 50,000 megawatts. Okay. There is another, say, 2,000 hours, between 2,000 and 400, where the demand varies from, say, 50,000 to 30,000 hours. Okay, so we will just plot these lines here as well. Okay, so this is like, say, two into 10 to the power 4. Okay, this point. Okay. So what we see is, let us separate these plots out into multiple segments. Let us eliminate this. We will see why we are doing this shortly. So this is, know that this is megawatt and this is hours. So if you integrate the area under this curve, you get the total energy that is being consumed by that state or city over the entire year in terms of megawatt hours, correct? And what this plot is basically showing is, there are certain segments over this energy demand, that there are certain periods of the year which are accumulated together where the hourly demand in power is quite high, between 70,000 to 50,000, and there are other regions where the hourly demand is significantly lower, like between, say, 2,000 to 3,000, somewhat here. Okay, and this area under this curve is the total electricity consumed by that location over the entire period of year. Okay, and here is the region of intermediate demand. And below this is the region of base demand. So here is the region of peak load. Okay, this is the region of intermediate load. And this is the region of base load. Okay. So let us look at this idea in three segments. The base load is around 20,000 megawatts, and this is the power demand that is always present over the entire 8,640 hours of the year for that community. Okay. The intermediate load is between 20,000 and 50,000 megawatts, and it is varying over this area. There are certain regions where the demand is much lower, like say below 3,000, 30,000 megawatts. There are other periods of the year where the demand is between 50,000 and 30,000 megawatts. And this area of the electricity consumption is being delivered to by the intermediate load or the cycling power plants that are being turning on and off to cater to this variable intermediate load demand. Okay. And then at the top, a much smaller section of the total energy requirement is the peak load, which is varying from 50,000 to 70,000 megawatts. Okay. And this peak load is only present for a few hours over an entire year. It is only during this time that the peak load power plants are operational and at various fractions. Okay. So basically what this means is, if you look at the power plant population, the base load power plants are always on. The intermediate load power plants come on and off with a they come on during when the demand rises and then turn off when the demand falls. And the peak load turns on at the rarer occasions when the demand goes to the very high levels that are shown here. Okay. So here basically peak load power plants operate when demand rises above 50,000 megawatts and supplies only 3 to 4% of the total electricity consumed. Okay. Intermediate load power plants operate when power demand exceeds 20,000 megawatt and contribute 20 to 22% of electricity. Consumed. Okay. Base load power plants cater up to 20,000 megawatt demand and contribute to 75% of the electricity. Okay. Now, the important thing here to note is the base load power plants are extremely efficient. So 1 megawatt of base load electricity is delivered relatively cheaply. The intermediate load power plants are less efficient, though still efficient enough, and so 1 megawatt of intermediate load power plant cost is somewhat higher than the base load electric power. And the peak load power plants are significantly more costly, and hence 1 megawatt of peak load power plant may cost significantly more than base load or intermediate load power plants. Okay. So the cost of 1 unit of electricity is not constant even in a given day. It is variable, and the variability depends on which type of power plant is being used to generate that unit of electricity. It is why you will see that in most electricity bills there is the cost of electricity increases if the amount of consumption increases. So below a certain consumption units, the cost is low. Above that certain consumption unit, the cost becomes progressively higher. Because what this means is your demand is increasing, so the probability that if you are consuming that much electricity, those electrical units are coming from the peak load or the intermediate load power plants, and hence the cost is higher. So that calculation is being taken into account. What this also means is that the role of a new type of power generation system, like a renewable power generation system, is cost competitive with a traditional power generation system at different levels. So suppose you have a grid where only 10% of the electricity is coming from a renewable resource, like a solar energy is contributing say 10% of the electricity. That 10% is usually coming in the peak load and the upper regions of the intermediate load graph here. Hence, they are basically replacing the more costlier peak load and the intermediate load traditional power plants, and hence you can have that electricity unit come at a somewhat higher price than a traditional base load power plant. Okay. So it remains economically viable at 10% penetration. Okay. However, if the renewable energy amount increases to say 40 to or 50% of the grid, then that renewable energy system is not only catering the peak load and the intermediate load, but is also catering to part of the base load. So then that renewable energy resource has to be significantly more cheap than what it would have been if it was only giving 10% of the electricity, because otherwise the cost to the consumers is going to increase, because it is replacing extremely efficient and extremely cheap base load traditional power plants. Okay. This is the economic consideration. Another technological consideration is that a base load power plant is operating continuously and delivering an uniform amount of power throughout the year. So it's a uniform level, constant operation, reliable system. So the reliability of this new energy system, the renewable energy system, has to be as good for it to be a viable replacement for the base load traditional power plant system. It has to be reliable, it has to be consistent, it has to deliver power at an uniform level 24/7, and it has to be cheap. This is what is required if the renewable energy penetration into your electricity grid has to be 40, 50 or 60% rather than 10 or 20%. And this is the challenge that the renewable energy systems have to meet as we are replacing more and more of the traditional coal-fired units with these renewable solar or wind systems. And this is where there are certain problems. Problem number one, let us assume we are looking at a solar energy farm. Now clearly that farm will not generate any electricity whatsoever at night. However, as we have seen, there is a significant demand of electricity in the evening hours, and of course there is a base demand of electricity that is going on throughout the day. So if solar energy is to be a dominant mode of electricity generation for a nation, there has to be a way that it can deliver electricity to the grid at night as well when the sun is not shining. And this is where possibilities of storing excess electrical energy through batteries or other storage technologies becomes important, because it is only through those means that a solar farm can hope to deliver electricity at any level to the grid at night. And that also increases the cost of this energy, because as we will discuss, energy storage is not 100% efficient. You will lose a significant amount of energy through this storage and retransmission route rather than direct transmission without storage route. So you are losing a significant amount of electricity that was being generated, which means that the cost of electricity will also be increasing most likely. Further, there is an infrastructure associated with having a storage of sufficient quantity to make this a viable option. Another option is if you go for wind. Wind, of course, does blow at night, so it can take up the slack that a solar power plant farm has at night times. However, while wind does blow all times of the day, it does not blow at the same magnitude. And we saw that the wind power is dependent on the cube of wind velocity. So if the wind velocity falls by just a little, the amount of wind energy that is being generated can decrease significantly. So wind power suffers from what is called intermittency. We will discuss these ideas as we go along, that the power generated fluctuates a lot because wind velocity itself is fluctuating a lot. Of course, if the wind velocity is above the rated velocity, as we discussed during the wind power classes, it will generate a constant power. So at least we need to cite the wind farms where most of the times the wind speed is above the rated, equal to or above the rated velocity. Otherwise, the wind energy that is being delivered will be lower and will be variable in nature. And in case you cannot ensure that 100% of the time the wind will blow above its rated velocity. It's just a probability aspect. So there also we need some sort of a stabilization technology or a storage technology which can store excess electricity when there is a lot of wind and then push that electricity into the grid when the wind drops and the wind farms cannot produce the electricity that is wanted by the grid. So you see, two of the most important renewable electricity generation systems, sun and wind, requires some auxiliary systems to make up for the absence of these resources or the variability of these resources that is extremely detrimental to the grid if these renewable energy systems are going to penetrate the grid in any significant segment. If it's just the peaking and the intermediate load, it's not a problem because those are turning on and off relatively less. They are asked to deliver power at relatively lower number of hours a year, so we can cater to the intermittency aspects by only turning it off when it's not required. So the problem is somewhat lower. But at higher penetration, we need to solve these problems, and this is where things like energy storage and smart grid and switching between different renewable resources intelligently becomes important. I discussed only water like wind and solar. We did not discuss hydroelectric systems, but the same problem does exist to a certain level in the hydroelectric systems as well. If you look at the Indian context particularly, both in winter and in summer, the amount of water in the rivers are quite low. It is only during the rainy season that the rivers have a significant amount of water flow, especially in certain parts of India which are not perennial river systems. So clearly a hydroelectric plant's power generation capacity is seasonal in nature. So while it will generate a reasonably constant amount of power throughout a day in a given season, the power that it can generate will change from one season to the next. So in a summer, when you have a large AC demand, the rivers may be running dry and hydroelectricity cannot cater to that demand. Similarly, in winter when there is a large heating requirement. So even hydroelectricity, even though it's a more uniform power generation system, does suffer from seasonal problems. So this is a kind of a common problem for many of these renewable resources where the variability of the presence of resource cannot be controlled by humans, and hence we have a problem of the demand supply matching. So let us discuss these ideas one by one. Sorry about this. So we will just summarize these ideas. Renewable energy resource like solar, wind, hydro suffer from diurnal and seasonal intermittency and hence their power supply is variable in nature and may not be synchronized with changes in demand. So an example will be sun does not shine at night, so solar farms cannot generate electricity during evenings and night times. Wind farms suffer from variability in wind velocity that affect the power generated by them. Hydro power suffer from seasonal variability due to change in water level of rivers. Okay. Hence, the need for technologies like energy storage that can store energy at times of high supply and release energy at times of high demand. Okay. So this is why energy storage systems are becoming a very important part of modern renewable grid infrastructure. So in the next few classes, we will discuss various types of energy storage technologies, and we will show how these energy storage technologies, how their efficiencies are, what their physical, the way this storage is happening physically, and what their applications are in various aspects of the grid. Okay. So that will be the focus over the next few classes as we move into our discussions. So we will stop here today. Thank you for listening, and we will come back in the next class. Thank you.